Dipole moment is a way that we designate the polarity of a bond, and it shows the direction of the relative negative charge. So here are a few ways that we can represent the bond polarity and actually talk about the overall polarity of a molecule. So what we have is, so this is just a symbol which shows the charge. So it has a partial positive charge where the hydrogens are and a negative charge for the oxygen. And then this is what the previous slide was talking about. So the arrow points toward the negative side of the molecule, and the positive, or the cross part there, is for the more positive side. And then you also see that in an electrical field that the positive side is going to be attracted toward the negative plate, and the negative side is going to be attracted to the positive plate. Then we have this electron density representation, which is nice, and it shows the different regions around the molecule, and the more positive side here and the more negative side. So it's really just three different ways to express the same idea. And it is possible to calculate dipole moment and to use those numbers, but we don't really use that too much. It's just an idea that helps us understand the polarity of a bond and also the polarity of a molecule. So if we look at a different molecule like carbon dioxide, what we see there is that the bond itself is polar, but the dipole moments cancel each other out. So for those of you who are in physics and you've talked about vectors, this would be the same sort of concept. So the vector has a magnitude and it has a direction, and if the two magnitudes are equal but opposite, then the overall charge, or the overall dipole, cancels out. And then if you look over here, you can see the same sort of electron density representation, which is another way to express the same sort of idea. So to summarize, it's possible for bonds to be polar and to still have a nonpolar molecule. So one way to think about how stable compounds form is to assume that they gain a noble gas configuration, and they can do that either by losing electrons or gaining electrons, depending on what they're bonding to and also their position on the periodic table. The basic idea here is that nonmetals tend to form bonds that are based on sharing electrons, which is called a covalent bond. And when we have a compound that forms between a nonmetal and a metal, then the attraction is due to the ions that are formed when those particular atoms either gain or lose electrons, and then they're held together by the difference in charge. So that's referred to as an ionic compound. A term that comes up when we're talking about electrons and electron configurations and configurations of ions is what is referred to as an isoelectronic series, and that just means that it's a group of atoms that have gained or lost electrons, and they have the same configuration. So it's important to remember that, for example, when fluorine gains an electron and becomes like neon, that means in terms of its electron configuration, it still has a different number of protons. It's still fluorine, or the fluoride ion, but it is the same in terms of the electron configuration. So in this case, we are looking for an alkali metal, an alkaline earth metal, noble gas, and a halogen that will form an isoelectronic series. So just to pick something different than we looked at before, we could look at argon. So if we write out the configuration for argon, that's 18, and so the configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. and that's going to give us 18, so that's 18 electrons. Okay. So all of the configurations for the isoelectronic series will have the same, so you're going to have the same configuration, the same number of electrons. So what will those be? So if you have the halogen that's closest to argon, that's going to be the chloride ion, so that's 1. And then if you go 1 up from that, that's going to be potassium. So potassium normally has 19 electrons, and then it loses an electron to become similar to argon. And then if we look at one more, that would be calcium, and calcium is 2+. Now the number of protons is fixed, so the number of protons are fixed for each particular element. So argon has 18, chlorine has 17, potassium has 19, and calcium has 20 protons. We already talked previously about trends in properties such as atomic size, ion radius, ionization energy, and electronegativity, so the periodic table is useful for getting that information, also obviously for the electron configurations, and it helps us to predict formulas for ionic compounds based on this idea that the atoms are going to achieve a noble gas configuration. And it's also useful for comparing covalent bond strengths, and we did some work on that back in section 8.2.